Testing. 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 Come on, why is this not turned on? Testing. Testing. Okay. Come on, why is this not turned on? It's working. We're good. We're live. Alrighty. Welcome everyone to another Hoopo stream. Hope you guys had a good weekend. We are going to start off this week with a paper called Neuralangelo. This is a paper out of NVIDIA Research and Johns Hopkins University. So we present Neuralangelo, a framework for high-fidelity 3D surface reconstruction from RGB images using a neural volume rendering approach. So, obviously 3D surface reconstruction means a mesh, which is a bunch of triangles with vertices and then edges connecting those vertices. RGB images, this is just the standard type of images you would get from your cell phone, right? There's a red, green, and a blue color channel, and then neural volume rendering is the technique behind NeRFs and a variety of other approaches, but basically the idea of using neural nets to render a 3D volume, right? So a volume is just a 3D space. Even without auxiliary data such as segmentation or depth, so segmentation is whenever you take an RGB image and you cut it up into different areas, usually corresponding to different semantic concepts, such as maybe background or foreground is the easiest one, and then depth. Sometimes you'll see an RGBD, and what that means is that there's a depth channel, and depth is can be done implicitly or explicitly. So implicit depth would be the depth that you get from a stereo camera. Explicit depth would be the type of depth that you get from a structured light sensor or a LiDAR or something like that. There's different ways to get depth, but it sounds like they're not going to be using any of those crutches. And here we have the 3D mesh for a courthouse. This is the actual mesh here, kind of with just the lighting. And then here you have the surface normal. So the normal vector is anytime you have a surface, you have the vector that points basically outside of that surface like that. And whenever people do these normal images, really what they're showing you is the direction of that mesh. So obviously green is upwards, and then red kind of faces us, and then blue faces that way. So you can see how, for example, this column here goes from red to blue as the normal vector rotates around that column. All right, so they actually have a really nice little supplementary kind of web page looking thing where they kind of nicely summarize this. So let's go ahead and kind of quickly scroll through this, and then we'll go back to the paper. Neural surface reconstruction has shown to be powerful for recovering dense 3D surfaces via image-based neural rendering. Is this the same as this abstract? Yeah. However, current methods struggle to recover detailed structures of real-world scenes. Yeah, so kind of the name of the game in surface reconstruction is how detailed can you get? Can you get in between the cracks? Can you get the things that are occluded? There's a lot of different details that are generally lost, so there's still a lot of work to be done in terms of making algorithms that are better and better at surface reconstruction. To address the issue, we present Neuralangelo, which combines the representation power of multi-resolution 3D hash grids. So a hash is a map, and it's a mapping between a key and a value, right? So if you guys are familiar with Python, a dictionary is actually technically a hash map, which is mapping the key, which is usually a string, into a value, which, I don't know, maybe it's like a number or something like that. But a 3D hash grid is basically kind of the same idea. Think about a table where there's some kind of key, which basically is the 3D position, some kind of 3D position in space, and that maps to some kind of value that you're storing there, right? So it's basically like you index an entire 3D volume, and then you can quickly access things inside there. Multi-resolution refers to the fact that there's going to be different sizes of the way that this hash map is created with respect to the volume. So maybe you'll have a coarse resolution, then you'll have a fine resolution, then maybe an extra fine resolution or something like that. Two key ingredients that enable our approach: numerical gradients for computing higher order derivatives as a smoothing operator. Okay, so numerical gradients are different from analytical gradients. So analytical gradients, think about that as actually solving and actually basically sitting there with the equation and calculating the exact derivative of some kind of function, right? And that's basically the analytical gradient. Numerical gradients, think of that like you basically have a point, you take the kind of like slope at that point, and then you sample slightly above, and then you sample slightly below, and then you basically get an estimate of what the gradient is, right? Let's see if I can find a picture of this. But yeah, when I think numerical gradients, I think of basically this Newton's method, where you're basically like approximating the slope of a line by basically sampling at new points and then plugging in a number and then seeing what the kind of slope is between those samples. So the TLDR is that numerical gradients are generally faster and easier to compute, especially if your function that you're trying to take the partial derivative of is complicated, but they're also inaccurate fundamentally. So there's a trade-off there. For computing higher order derivatives, so you have obviously your derivative, you have your first derivative, then you have your second derivative, your third derivative. So anything beyond the first is a higher order derivative, right? So velocity is the first derivative of position, and then acceleration is the second derivative of position, or the derivative of velocity. So it's a higher order derivative to position. And then smoothing operation, I don't know, that's a very generic term. That can really mean anything. It's just some kind of function that smooths out a set of curves. I don't know. Coarse to fine, so here's the multi-resolution aspect. So kind of confirming here that there's going to be multiple stages here. Optimization on the hash grids, controlling different levels of detail. Yeah, okay, so very clearly at least going to be two, a coarse and a fine, but I bet you there's probably even more levels of that. There might even be 3 or 4 levels. Even without auxiliary inputs such as depth, Neuralangelo can effectively recover dense 3D surface structures from multi-view images. So there isn't necessarily a formal definition here for the word dense, to be honest. Like, you know, dense 20 years ago means a different thing than dense nowadays. Dense basically just means that there's a lot of points, and obviously if you want to have a lot of detail, you're going to need a lot of points. So fidelity significantly surpassing previous methods. So hopefully they show us some benchmarks. Enabling detailed large-scale scene reconstruction from RGB video captures. So here you go. Finally, they're telling you. Here they say RGB images, but of course video is just a series of RGB images. You could think of it just as a sequence of RGB images. All right, so pretty straightforward abstract there. I think we have a pretty good idea of what we're doing. Let's look at some of their stuff here. Here you have, I guess, the input video is this picture of a house, and they're showing you how good the details are. Obviously, you see all the little chips, all the little edges and holes and nooks and crannies on these objects. I don't know what this is. Veritas Libert. I think this is the Harvard building. I don't know. Oh, okay. These are really cool. Yeah, I like these. We'll go back to these when we're looking at the math. But here they have some comparisons to a couple different approaches. And you can see how, for example, here neural wrap or neural warp, you can see how there's holes in this mesh. There's obviously issues. There's artifacts here. You see how this kind of edge looks a little weird. But here in their method, Neuralangelo, it looks quite smooth. It looks quite crisp and clean and complete. Obviously, these examples are going to be cherry-picked, so take that with a grain of salt. They probably did this for 20 things, and then these are the best-looking ones out of all of these. This one actually looks worse. So Neuralangelo here, it looks a little bit less smooth than the neural warp, so I guess the neural warp messes up here, so you see this area here where there should be a hole. Neuralangelo does well versus neural warp actually just creates this almost like a flashing. If you guys have ever done miniatures, that's a word from that niche. Okay, let's get into this paper. This paper is quite long, so we're going to have to get going. 3D surface reconstruction aims to recover dense geometric scene structures from multiple images observed at different viewpoints. The different viewpoints is a key here because obviously you don't know what you don't know. So if you don't have a view of the back of this building, it's basically going to be impossible to reconstruct the back of the building. So just inherently any kind of RGB images or RGB video that you use for reconstruction, you're going to need to have it at a bunch of different viewpoints. The recovered surfaces provide structural information useful for many downstream applications such as 3D asset generation. So once you have a mesh for this, there's no texture on this mesh. That's one thing to notice. Usually assets, right? Assets refer to the actual objects in like a video game, but there's no mesh here, right? Usually you have a mesh and then you have a texture, which is kind of like a picture, right? Like a PNG image that like wraps on top of this, but I don't see a single texture here. So far this is just meshes. Or environment mapping for autonomous navigation of robotics. Obviously you probably don't need meshes for autonomous navigation, but you definitely need meshes for augmented and virtual reality. Photogrammetry is the process of generally doing this. There's a subreddits for photogrammetry, people who love to kind of scan things and make 3D objects, so definitely check that out if that's your interest. Using a monocular RGB camera. Monocular means it's a single RGB camera. It's not part of a stereo rig or something like that. And it's harder to do that because if you don't have a stereo, then you don't have an implicit sense of depth. As it equips users with the capability of casually creating digital twins of the real world using ubiquitous mobile devices. Yeah, and there's kind of like a battle going on, right? Where on one hand, having multiple cameras and depth sensors is going to make it better for photogrammetry, and you see a lot of cell phones are moving in this direction. I think the latest Apple cell phone and the latest Pixel cell phones have actual depth sensor in them, which means that they can give depth, and that means that the algorithm that you use to reconstruct objects can be much better. But then on the other side, the algorithms themselves are getting better and better over time. So here, obviously, this algorithm, they're kind of showcasing that they don't need multiple cameras, they don't need a depth sensor, they can just reconstruct using entirely monocular RGB images. So there's this kind of back and forth where, hey, do we need the camera on these mobile devices to get better? Do we need more cameras? Do we need depth sensors? Versus, hey, can we just rely on the algorithms getting smarter and smarter over time, and then we can just continue to have a cell phone that just has a single camera on it? Okay, classically, multi-view stereo algorithms have been the method of choice for sparse 3D reconstruction. Obviously, stereo, now you can get the depth, which means that it's going to be a lot easier to do 3D reconstruction. An inherent drawback, however, is their inability to handle ambiguous observations, regions with large areas of homogeneous colors. Yeah, so this is a very common problem in the classic stereo disparity algorithm. So basically, if you have a stereo camera rig and it's looking at some white wall, right, it's very difficult to know if that white wall is a white wall that is 2 inches away from your face or if that white wall is a wall that is 10 miles away from your face, right? You need to have basically these corresponding points in a stereo image in order to be able to say, okay, well, this point corresponds to this point, and the distance between those 2 points, and my camera space is this, and I know how far away my cameras are, therefore I know how far away these objects is, right? So the actual texture of the area is important for multi-view stereo in order to get the depth from that. This would result in inaccurate reconstructions. Recently, neural surface reconstruction methods have shown great potential, right? So neural networks and deep learning making a big stride into surface reconstruction. This new class of methods uses coordinate-based multi-layer perceptrons. Multi-layer perceptrons, just a fancy word for a fully connected neural net. So just in your head, think about a bunch of neurons all connected to layers above them. Coordinate-based, that could refer to the coordinates of the hash map. It could also refer to the coordinates of the multi-view. I'm not sure exactly what they're talking about there. To represent the scene as an implicit function. Okay, so this is actually what a NeRF is, right? Occupancy fields. Occupancy refers to inside a volume, whether or not the part of that volume is occupied, right? So you have some square, some volume in 3D space, and then what is the occupancy at any point within that volume? Sign distance functions. This is a function that tells you how far away you are from the surface of an object at any point inside a volume. This is separate from NeRFs, but they've become very popular as well. We've read a couple papers on this channel where they use SDFs in order to get these meshes and surfaces. Leveraging the inherent continuity of MLPs and neural volume rendering, these techniques allow the optimized surfaces to meaningfully interpolate between spatial locations, resulting in smooth and complete surface representations. Yeah, so the keyword here that you want is you want smooth and complete, right? So you want smooth, as in you want the actual, you don't want any of this kind of like weird jagged bumpiness, unless of course that is the actual way that the surface looks. And then complete is you don't want any holes, right? So for example here, I guess this is overcomplete, but this one here, right? This has a hole in here. You wouldn't want that hole, right? Not complete versus here, complete. And actually, the placing of this, this is probably due to reflection. So I bet you what happened here is that this part of the apple is actually shiny, and so you had some weirdness there, right? But you see how the Neuralangelo compared to Neuralwrap, it's able to find that hole. Despite the superiority of neural surface reconstruction methods over classical approaches, the recoverative fidelity of current methods does not scale well with the capacity of MLPs. Okay, so capacity of MLPs, I guess what they're saying here is that you can make these MLPs, these multi-layer perceptrons, bigger and bigger. These are bigger neural nets, and it doesn't seem to, does not scale well. So it doesn't seem like you can just take the algorithms of 2 years ago, scale up the multi-layer perceptron, and get way better performance. So they're kind of hinting at the need for a better prior or some kind of better pipeline or system in order to get the performance that you want. Instant NGP, I think this is also an NVIDIA paper, but it might even be the same guy, Mueller et al. Is that the same guy? Yeah, I bet you that's this guy. So there you go. Thomas Mueller has been working on this for a long time. Instant NGB produces a hybrid 3D grid structure with a multi-resolution hash encoding and a lightweight MLP. Yeah, so this hash map at multiple resolutions, I think that's not necessarily new to this paper. I do remember seeing that in a earlier NVIDIA paper, so that's something that they've kind of been pioneering and then kind of pushing forward. Enables a lightweight MLP that is more expressive with a memory footprint log linear to the resolution. So one of the problems with the multi-layer perceptron, especially for something like a NeRF, is that you have to basically perform inference on this MLP at every single pixel in your image, and that becomes very expensive, especially if you have a very large MLP. So much like they said that not only does it not scale well, right, with the capacity of the MLPs, but I guess that's exactly what they mean, is it does not scale well with the capacity of the MLP because the amount of inference you need to do for a NeRF is actually pretty huge, right? Especially if you have a lot of pixels, you have a big image. So keeping that multi-layer perceptron within the NeRF is keeping it very small is important. The proposed hybrid representation greatly increases the representation power and has achieved great success at representing very fine-grained details for a wide variety of tasks such as object shape representation and novel view synthesis. Okay. We propose Neuralangelo for high-fidelity surface reconstruction. Neuralangelo adopts instant NGP and a neural SDF representation of the underlying 3D scene. Okay, so basically it seems like maybe the big part of this paper is going to be combining this hash map from the NGP into the SDF kind of family of approaches, optimized from multi-view image observations via neural surface rendering. We present 2 findings central to unlocking the potentials of multi-resolution hash encodings. First, using numerical gradients to compute higher order derivatives. So, right, this idea of rather than using analytic gradients and like actually computing the derivatives, you basically just get these approximations of the gradients by using numerical methods. Numerical as in basically numerical approximation. Such as surface normals for the iconal regularization. Okay, so obviously surface normal is the surface vector. I don't really know what iconal regularization is, but some kind of, generally when you see regularization, it's some kind of additional constraint or prior that you're adding to your optimization process that regularizes it, right? Like makes it more stable and it generally converges better towards the answer that you want. Is critical to stabilizing the optimization. A progressive optimization schedule plays an important role in recovering the structures at different levels of detail. Okay, so progressive optimization schedule there, that's telling me that this optimization process is going to have likely a bunch of different steps, and then as the steps go further and further, there's going to probably be a bunch of different hyperparameters, possibly the hyperparameters that control how much these regularizations are impacting the process. So I don't know, that's not necessarily good when you see that because it means that it's more complicated than you think it is, right? Different levels of detail. We combine these 2 ingredients and via extensive experiments on standard benchmarks demonstrate significant improvements over image-based neural surface reconstruction methods in both reconstruction accuracy and view synthesis quality. Okay, so we'll see whether or not this actually gets better. All right, and then here at the end of the introduction, so generally in a machine learning paper, you have the end of the introduction contains a bulleted list of all the key contributions of this paper. So if you're ever in a huge hurry and you don't have time to read the paper, you can basically just read the end of the introduction. You find these bullet points and you have a good idea of what's going on. So they present the Neuralangelo framework to naturally incorporate the representation power of multi-resolution hash encodings and neural SDF representations. So basically they're going to be combining this multi-resolution hash encoding idea, which is also an NVIDIA idea, with basically the SDF, the sign distance function. We present 2 simple techniques to improve the quality of hash encoded surface reconstruction: higher order derivatives with numerical gradients and coarse-defined optimization. Okay, so this is the kind of optimization schedule that they were talking about, where I guess they're going to be starting from coarse and then eventually moving to finer and finer details. So, and then the higher order derivatives using numerical gradients, which probably makes things faster. We empirically demonstrate the effectiveness on various data sets, showing significant improvement. All right, so they combine 2 ideas, and then the last bullet point basically says that they extensively test those ideas. All right, let's get into this related work here. Let's see, are we at any point here anymore? No, we're still here. Okay, let's go back. Multi-view surface reconstruction. Early image-based photogrammetry techniques use a volumetric occupancy grid. So occupancy means whether or not there's a point in that volume. I kind of need like a, actually wait up, this might even be better. Yeah, so you could think of this as a grid, right? And then within this grid you have basically, these are called voxels usually, right? A voxel of your volume. And then you have a point within this voxel. So this voxel here would not be occupied. This voxel would be occupied here, right? So that green dot is a point on the actual mesh. Each voxel, right, where voxel is one little square within that volume, is visited, and it would actually be a cube, my bad, because it's 3D, it's not a square, it's a cube, is visited and marked occupied if strict color constancy between the corresponding projected image pixels is satisfied. Okay, so basically if you have, this is image-based photogrammetry, so it's going to be 2D images of the actual real thing. If you take each pixel at each of those 2D images and you project them into that 3D volume, and then you're like, the color inside this voxel corresponds to the color of the image pixel, then therefore there should be something inside this voxel. The photometric consistency assumption typically fails due to auto-exposure or non-Lambertian materials. So this just refers to weird situations. Obviously, this auto-exposure, right, if we actually go back to this, I bet you that's what was happening here, right, where the reflection of the apple right there is what caused the issues. I'm not sure what non-Lambertian is. That might mean see-through. Let's see. Non-Lambertian surface is a surface that does not reflect light uniformly in all directions. Okay, so basically just some kind of weird material property. Mirrors, corner cubes, machined surface with some kind of structure and roughness. Okay, so basically you got weird surfaces and weird reflecting properties, then any kind of photogrammetry-based technique is going to have a hard time, because photogrammetry relies on looking at the different parts of the object and being able to say this part of the object corresponds to this part of the object. But if the reflection of the light changes the appearance of the object depending on where you're looking at it from, then it's going to be very hard to do that kind of correspondence. And they call this the consistency assumption. Relaxing such color constancy constraints across views is important for realistic 3D constructions, right? So they're basically saying this prior that all photogrammetry techniques have of consistency assumption is probably not a good prior to have. So if we can get rid of that prior, then we'll be good. Hello, Kalina. Non-Lambertian sounds like a matte surface. Yeah, the inverse. So there's a lot of different properties for surfaces, especially if you're in the 3D asset video game kind of world. You might be more aware of this, but there's like roughness, specular. There's like ways to make them see-through. There's a whole world of kind of material properties. Okay. Follow-up discussions or follow-up methods typically start with 3D point clouds from multi-view stereo techniques. So 3D point clouds is, I think it's easier to explain what a point cloud is by just looking at a picture of a point cloud. You've definitely seen these before. It's basically this, right? So, right, you have a bunch of points, and all those points are in some kind of global frame, and they correspond to some kind of real world scene. This is not a point cloud. This is a point cloud, right? This is a point cloud from a autonomous vehicle, and autonomous vehicles have these LiDAR sensors that basically spin on the top, and that's why whenever you look at a LiDAR or a point cloud from an autonomous vehicle, it has that kind of these kind of like circles that go around like that. That's because there's this kind of rotational symmetry to the sensor itself, where the sensor itself is spinning, and that's why you get these kind of like weird like circular artifact. All right, this is another good example of that artifact there. Okay, reliance on the quality of the generated point clouds often leads to missing or noisy surfaces. Recent learning-based approaches augment the point cloud generation process with learned image features and cost volume construction. However, these approaches are inherently limited to the resolution of the cost volume and fail to recover geometric details. So there's a little bit of kind of a war going on, to be honest, between in the robotics and kind of autonomous vehicle space about whether or not you need to use point clouds and sensors that give you explicit depth, like a structured light sensor or a LiDAR that you would have in a car. So famously, for example, a Tesla car has only RGB cameras, and I'm actually on Team Tesla on this one. I don't think that point clouds are good. You know, I've actually used a bunch of structured light sensors in a bunch of different projects, and every single time it was terrible. They suck at different material properties. If you change the lighting, it completely fucks it up. So I just feel like point clouds and any kind of LiDAR-based sensor is on its way out, and I don't see a world where 10 years from now we're still using these LiDAR sensors. I feel like cameras are so cheap, they're so ubiquitous, and I think that with just a little bit of extra effort, we can get all these algorithms to work without any kind of explicit 3D depth. So, I don't know, my potentially controversial opinion is that point clouds are a thing of the past, and we'll be moving more and more into basically just pure RGB image-based approaches, and you won't have to get these structured depth, or not structured depth, but explicit depth sensors. Okay. Neural radiance fields, everybody's favorite neural network for 3D. NeRFs achieve remarkable photorealistic view synthesis with view-dependent effects. Right, so a NeRF encodes a 3D scene with a multi-layer perceptron mapping 3D spatial locations to color and volume density. So, let's see, I'm just like reading this so I can, maybe they define NeRFs better than I do. Pixel colors using neural volume rendering. All right, so we're bringing out the NeRF picture here. NeRF, hopefully it's the actual NeRF and not like the NeRF toys. Yeah, this is the problem, is if you type NeRF, more often than not, it's going to be the pictures of the NeRF toys. NeRF computer vision. Yeah, here you go. This is the pic that I want. Open image in new tab. So what a neural radiance field is doing, it's a little multi-layer perceptron. So here you see this F theta here. This is a little neural net. And this little neural net, it takes in a couple different things. It takes in X, Y, and Z, which is the X, Y, and Z position of this little point here. It takes in a theta, and a phi, which is basically a view angle. So it needs to know where are you looking at this little point from. And then you say, okay, well, I'm looking at this little point, and I'm looking at it from this direction over here. And what this neural net will tell you is, okay, if you're looking at this point from this direction, this is what the color of that point is, right? R, G, and B. And then this is how the opacity, or basically how see-through is that point. So what this little neural net is doing is it's basically encoding implicitly this object, right? So NeRFs are very interesting because you can basically encode a scene in the weights of a neural net, and you can reconstruct images from that scene, right? So I can get this image of this little truck and this image of this little truck without having a mesh and a texture and any kind of explicit representation of like, this is the object and this is the boundary of the object and so on. All I need to do is basically just say, okay, well, I have this ray. I'm going to be looking at it from this direction. I'm going to sample points along this ray, and then which one of for each of these points, what is the color and the opacity of that, right? So here, obviously, you're seeing the neural network is telling you here it's a bunch of see-through, see-through, see-through. Now it's an orange, then it's a darker orange, then it's see-through, see-through. So then you can say, okay, well, I guess this pixel here is this slightly yellow orange combined with this slightly red orange, and then there you go. And that final little step there is called a ray marching algorithm, and this is how you render a 2D image from a neural radiance field. But neural radiance fields are a very powerful idea and powerful concept. They've become kind of their own kind of branch and kind of thread of machine learning research. And I honestly feel like they're the future. I feel like even though it feels science fiction-y, I feel like we're going to move into a world where we don't have to have explicit explicit meshes and textures and any kind of like basically explicit 3D representation. I think we're going to actually move into a future where everything is NeRFs. And as weird as it sounds, I can envision a world where your VR headset doesn't store any assets. It's just rendering NeRFs as is. Okay. So that's what a NeRF is. The problem of NeRFs is the question of how an isosurface of the volume density could be defined to represent the underlying 3D geometry, right? So the problem with this is that you don't have an explicit representation of the underlying geometry, right? If I gave you this NeRF, if I gave you a file that just contained the weights of this neural net, you would have no idea what kind of object this represents, right? You'd have to actually render it from a bunch of different views in order to get 2D images of the object. But if you wanted to do maybe some kind of physics, or maybe you wanted to put this in a video game right now, you'd have to figure out how to get an actual mesh and an actual texture, right? So a lot of works are trying to solve that problem of, okay, how do I take a NeRF, which is a great representation of an object, but convert it into this kind of explicit representation that I need in order to actually import it into a game world, right? And that's where the signed distance function, this SDF, these techniques are coming in. Due to insufficient constraints, the surfaces are often noisy and may not model the scene structures accurately. So a lot of times the problem with NeRFs is that you get this kind of like almost like a hazy effect, NeRF fuzzy effect. Jesus Christ, my Googling techniques are awful. NeRF neural net. See that. Maybe this one? I think this one's kind of good. So, yeah, maybe it's not easy to see, but basically a lot of times you don't get like an actual crispy edge, right? The NeRF doesn't really necessarily have a good prior for representing surfaces in a very crisp and defined way, saying this is the beginning of the surface, this is the end of the surface, and there's a very clear kind of discontinuity here where the surface begins. NeRFs are a little bit more fuzzy, and oftentimes you'll see this kind of like almost like a misty, where it looks like there's a mist of like almost like a probability cloud of where the object could be, right? Direct modeling of the surface is preferred. And I think a huge reason why it's preferred is because game engines and any kind of like anything you would do with a 3D asset usually requires a mesh and a texture. You can't import a NeRF into Unity, for example. You would have to convert that NeRF into an asset, and then now you could import that asset into Unity, but as of right now, there's no way to import NeRFs into Unity just like that. Maybe there is. I don't know. Someone could correct me there. For scene representations with better defined 3D surfaces, implicit functions such as occupancy grids or signed distance functions are preferred over simple volume density fields, right? So this is kind of the same thing that we've been saying 10 times here in a row, where basically implicit, I would call these explicit. Am I getting my implicit explicit confused? I would say a NeRF is implicit because it's inside the actual weights of the neural net. You don't have the actual object itself. And then I would say occupancy grids and SDFs are explicit because you're like actually defining the exact position of this surface. So I don't know, maybe I'm getting my implicit versus explicit. My English is terrible. Explicit means something that is stated plainly, while implicit refers to something that is implied and not stated directly. Okay, so I would actually... Yeah, I think that I'm correct here, so I don't think implicit is the right word there. I would have used explicit. To integrate with neural volume rendering, different techniques have been proposed to reparameterize the underlying representations back to volume density. These designs of neural implicit functions enable more accurate surface prediction with view synthesis capability of unsacrificed quality. This is kind of an interesting adjective for the word quality there. Follow-up works extend the above approaches to real-time at the cost of surface fidelity. So another huge problem with NeRFs is that they're very slow, and the reason they're very slow is because you basically need to calculate every single one of these. So every single one of these points here is a inference, right? So for every single one of these points, you need to basically perform inference. So just think about that. For 1 pixel of this image of the Tonka truck, you need 1, 2, 3, 4, 5, 6, 7 different inference steps, right? And now imagine that, okay, well, that's just 1 pixel. Now I need to do that for however many pixels I have in this image, right? So there's this huge problem with NeRFs that they basically require a huge amount of inference. So there's been a lot of approaches that try to solve this of like, hey, how can we make this faster? So this real time means basically, can we do this fast? While others use auxiliary information to enhance the reconstruction results. Notably, Neural Warp uses patch warping, giving co-visibility information from structure from motion to guide surface optimization. Structure from motion is, I would say, kind of an older term at this point, but it kind of falls within the kind of like idea of like, hey, if you have a video and that video is a sequence of frames and you kind of know, maybe you have an IMU, maybe you have an accelerometer in your actual camera, so you know the exact motion of the camera from one frame to the next, can that help you basically determine the actual surface and the structure of the object that you're moving around with your camera? And hey, if you have that extra information, we can figure out how to put that into our algorithm, and that's probably what neural warp does. Neural warp is, I think, the technique that they're comparing to here. Yeah, this one here, neural warp. So neural warp does some fancy things to use the extra information of the motion in order to improve the surface quality. Other methods utilize sparse point clouds from SVM to supervise the SDF, but their performance are upper bounded by the quality of the point clouds. Yeah, so if your point cloud is shit, the actual reconstruction is going to be shit. So the use of monocular depth and segmentation as auxiliary data has also been explored. Monocular depth there refers to the fact that you can actually get depth from a monocular camera. This is called monocular depth estimation. So there's a whole family of approaches where basically given a single RGB image, can you reconstruct the depth? And the neural network is telling you what the depth is, right? So for example, here you have a scene of a car. Open image in new tab. You have this scene of a car, and then here's the depth, right? So obviously in a depth image, this black color represents stuff that's far away, and then this yellow color represents stuff that's close. So obviously these cars here are closer to you. That's why they're lighter colored. And there's a bunch of people that have used deep learning in order to basically say, given this image, give me this depth image. But the problem is that these type of monocular depth estimation techniques are generally very sensitive to the modality, right? So, or not the modality, but the distribution. So if you take this monocular depth estimation network and apply it to an image that isn't a car image, it doesn't work. At least I've tried to do that, and it doesn't work. They're very fragile. They pretty much only work for the kind of the type of data that they've been trained on. So that's what monocular depth refers to. And segmentation, obviously everybody knows what segmentation is, but segmentation maps. A segmentation map is like this. It's basically this one here. It's a picture that is separated into the different areas of the pictures that have semantic meaning. So here you obviously have some category for car, you have sign, you have person, you have road, and so on. So if you have depth, if you have segmentation, you can use that as auxiliary data to basically improve the performance of your surface reconstruction. So has also been explored, or using scene representations with hash encodings. In contrast, our work builds upon hash encodings to recover the surface without the need for explicit auxiliary inputs. And I think that's important, right? I think that there's a lot of approaches. Basically, this whole related work section, kind of what they're telling you is that it's very common for people to try to use all this kind of extra information, right? All the structure for motion information, the monocular depth, segmentation, explicit depth, different kinds of extra information, because it's such a hard problem. Surface reconstruction is such a hard problem that if you can find any extra information that'll help you improve it, then you can create a technique, and that technique will generally be better, right? So the impressive thing about this paper is that they're doing this not with it. They're not doing any of that, right? They're just using RGB camera images, and that's it. They don't have any structure for motion, they don't have any depth, they don't have any segmentation, and it still works very well. Concurrent work also produces coarse-defined optimization for improved surface detail, where a displacement network corrects the shape predicted by a coarse network. I think we might have actually even read this paper. This sounds familiar, but you have this kind of coarse-defined multi-step optimization. You have different neural nets doing different things. So you have a coarse neural net that gives you the coarse structure of the object, and then you have a neural net after that that corrects the coarse structure, and so on. So there's going to be a lot of different types of hierarchy being used in order to create these kind of more complicated pipelines. Hierarchy is not necessarily a good thing, to be honest, because to me it just means more complexity. Yeah, the reason people use hierarchy is because it works better, but if you didn't have to use hierarchy, You know, if you could just create the entire mesh in one go, that would be better than what they're going to do here, which is probably created in multiple goes, starting from a course and then iteratively refining it. Okay, approach. So that was the related work. Now we're going to actually get into the real math here, where they're going to explain exactly what they're doing. I'm actually kind of excited here. Neuralangelo reconstructs dense structures of the scene from multi-view images. Neuralangelo samples 3D locations along camera view directions and uses a multi-resolution hash encoding to encode the positions. The encoded features are input into an SDF MLP and a color MLP. Okay, so you have two different MLPs here. You have one for the SDF and then one for the color, right? So the SDF is the signed distance function. It's basically a number that represents how far away you are from a point or from the surface, right? So why is it signed? It's signed because if you're in front of the surface, it's positive, and then it goes positive, then it gets smaller and smaller and smaller. When you're right at the surface, it's 0, and then once you go into the surface, it becomes negative, right? So that's why there's a sign in that function. Okay, preliminaries, NeRFs. So let's see how good their explanation of a NeRF is. NeRF represents a 3D scene as a volume density and color fields. Along camera view direction, meaning we get some kind of camera chords when taking photos. Yes, probably. So the NeRF itself, right, it requires the actual view direction. So if you actually look at a NeRF, you need to know what the theta and the phi are, right? You need to know basically where the camera is. You need to know the camera position, and you need to know not only the position but also the exact orientation in order to know the exact position of this ray and to be able to sample inside your radiance field correctly. But anybody who's actually done photogrammetry knows that that's actually really hard, right? Because more often than not, you don't really know the exact position of the camera. You get basically approximations, right? There's a technique called Colmap, which is very popular. Which is basically given a video from your cell phone. It's a way of getting the position of your cell phone at every point in time when every single picture was taken, but it's not perfect, right? You don't know the exact position. So if you don't know the exact position of every single camera image, then it's going to be hard to use that information, right? There's noise in that information, so you can't necessarily trust it. Okay. NeRF represents the 3D scene given as a volume density and a color field. So the volume refers to this part here, this little sigma. That's the opacity. You can also think of it as how see-through it is. You can also think of it as the density. That's another way of thinking about it. And then the RGB is the color. So the color field is the RGB. Given a posed camera and a ray direction, so posed, there you go. You need to know the X, Y, Z position, and then also the orientation, right? The ray direction. The volume rendering schema integrates the color radiance of sampled points along the ray. So volume rendering is just the technique of, hey, once you actually have these points along the ray, how do you actually combine them together in order to actually create the value that you're going to put at this pixel, right? Because at the end of the day, you have a 2D image, and you need to be able to tell me what is the exact RGB color of this pixel right here, right there, right? Okay, the ith sampled position xi, okay, 3D position xi, at a distance ti from the camera's center. So what are we talking about here? We're talking about here I refers to the index here, so this would be 0, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7 if you're 1 indexing versus 0 indexing, and then the distance is basically the distance from this point here to the camera, distance from this point here to the camera, and so on. The volume density sigma I, right, so each one of those points is going to have a density, and each one of those points is also going to have a color, are predicted using the coordinate MLP, so the little multi-layer perceptron, which in this image is this f of theta here. This is the little perceptron, or multi-layer perceptron, and it's basically, it can take any point in this 3D volume, and it can tell you the color and the opacity of that point. The rendered color of a given pixel is approximated by the sum, and then here you have a nice little summation. This big letter E here means you sum from 1 to n, WI times CI, right? CI is the color, WI is this value here, TI alpha I, where alpha I is 1 minus the exponent of negative sigma I, which is the opacity, and delta I here, which is the distance between adjacent samples. So delta I is TI plus 1 minus TI. So going back to our picture here, delta I would be the distance between this sample here and this sample here, right? So you're taking the distance between those. That gives you delta I. You multiply that delta I with the opacity or the density. You basically do the 1 minus the exponent to get that nice exponent relationship there. And then you sum all of those up, or you multiply that by the color, sum all of them up, and that'll give you the actual color at a specific camera position. O refers to generally the origin of the camera, and then D probably the view direction of the camera. TI equals pi. This is a summation but product, so when you see this pi, this means multiply all this value here from j equals 1 to j equals I minus 1. So 1 minus alpha j is the accumulated transmittance. So generally what they mean by this is that because your TI is a property of basically the points before it, you have this kind of transmittance that's being accumulated, right? So go back to our thing here. As you're moving along this ray, you're accumulating a transmittance, right? You're kind of accumulating some kind of a transmittance, which is basically, you can think of it like the opacity, the density is similar to that, right? So there's a lot of techniques that people use, and one of the most basic kind of high-level concepts is that, okay, once you get to a certain level of opacity, right? Once you kind of get to a point where the opacity of this is very high, you don't really need to keep sampling along these points, right? The color of these points is not going to matter anymore because you can't even see them because basically they're blocked out by this point. So, indicating the fraction of light that reaches the camera. To supervise the network, a color loss is used between input images C and the rendered images C hat. Okay, so C hat is going to be a one color, right? It's going to give you a single pixel color. You're going to have a image that is composed of a bunch of pixels, and each of those pixels has a color that is calculated with this ray. And then you have your actual input images C, which are the images that you collected with your cell phone. And then what you obviously want is you want the difference between those to be as small as possible. So this double parallel lines here refer to the L1 loss. So here the 1, sometimes you have a 2, and that means that it's the squared difference between these, but here the 1 means it's just the rendered image pixel color minus the input image pixel color. Still having to have this kind of setup to use this thing is kind of a blower. As far as they use some kind of mega ultra camera setup to get those beautiful NeRFs in the original paper. Yeah, so unfortunately, like for most NeRF papers, when you actually look at the camera images that you need to have basically a uniform kind of like hemisphere of samples. And there's like an art to that, right? Like I mentioned a couple different photogrammetry communities, but within the world of photogrammetry, there's an art to that. There's people who like, they know exactly kind of like roughly how many pictures they're going to need and what kind of lighting you're going to need, and like exactly you're going to have to go around it and get every single color of it. And they even sell these like kind of like giant spheres that are filled with cameras, so you can put an object in it and get all the pictures from every view, and you know exactly where the cameras are. So there's this kind of notion of quality when it comes to the input images, right? You obviously want a lot of images. You want to know the camera position as exactly as you possibly can. You want to have as many images as possible. You want those images to be high quality, and you want the lighting to be basically as diffuse as possible. So that's really difficult to get with just like your hand and a cell phone, right? You're not going to be able to get the kind of camera position perfect. You're not going to be able to get every single thing. You're not going to sample kind of uniformly around the object. So it's still difficult to get good input images, and there's people who are very good at that. Surfaces are not clearly defined using such density formulation. Extracting surfaces from density-based representations often leads to noisy and unrealistic results. Okay. Volume rendering of an SDF. One of the most common surface representations is SDF. I don't know if I would call this the most common surface representation. I would say that meshes with vertices are more common than that, but SDFs are pretty common. So a surface S, surface is just, think of a mesh in your head, right? It's just like a flat surface in a 3D volume. Can be implicitly represented by its zero level set, i.e. a surface is the set here, the set of all points, right? And you see here this little like weird looking E, and then this kind of weird looking R with the 3. The R3 just basically means any position in 3D space, right? You have X, Y, and Z. That's where the 3 comes from. There's 3 dimensions of space, and then the fancy R just basically means all real numbers in there. So negative infinity to infinity for 3 dimensions. You have the surface is a set of points where this function is 0, right? So we were talking about the sine distance function where if you're ahead of it, it's positive. If you're inside of it, it's negative. And if you're right at that surface, it's 0. Well, that's basically what it means. Where f of x is the sine distance function. In the context of neural SDFs, proposed to convert volume density predictions in NeRF to SDF representations. Yeah, so people have been doing this where they've been using SDFs and NeRFs together with a logistic function in order to allow optimization within neural volume rendering. Given a 3D point xi and a SDF value f at xi, right? Your sine distance function can be evaluated at any point in 3D space. The corresponding opacity value alpha I. Ooh, I don't like that. I don't like that alpha I here refers to this here. Okay, no, never mind. I take that back. So alpha I is the opacity here. Sigma I is the density. Alpha I is the opacity. Okay, so at least alpha I means opacity in both of them. Is computed as alpha I is the max. Here you go. Phi s is the sigmoid. So phi s of f of xi minus phi s of f of xi plus 1. So why are they sigmoiding this? The reason they're sigmoiding this, right? Sigmoid looks like this. Apparently the sigmoid is also a part of the colon. Today I learned. All right, but the sigmoid will basically squash a function to specific bounds, right? So here between 0 and 1. So what they're saying here is that technically the sine distance function here can be negative infinity, it can be infinity, right? So you don't want to deal with a number like infinity or a number like negative infinity or some really big number. So they're going to put it into the sigmoid in order to make it basically between 0 and 1, so it's nicely shaped, right? So they take the value of the sine distance function at some point, and then at some other point, they put both of those through the sigmoid. They subtract, also divide by the sigmoid of that, and you get a nice little number there. And that is your opacity, right? And the opacity cannot be negative, so you cannot have negative opacity. So they say the maximum of whatever this ends up being and 0. So basically, if somehow you get a negative number out of this, your opacity is just going to be 0, which represents a see-through, or there's nothing there. In this work, we use the same SDF-based volume rendering formulation. Okay. Multi-resolution hash encoding. Isn't that a kind of derivative formula? So you're saying this is the derivative of something? Yeah, you're saying this exactly right here? Maybe, I don't know. Also, part of these, sometimes people use sigmoids and exponentials because they also want the sigmoid function multiplied by 1 minus that. That's what the derivative of the sigmoid is. Right here. Yeah, so maybe it kind of is, right? You can kind of see that. I can kind of see how this would maybe look like the derivative. I don't know. I don't know. I don't know what the sigmoid derivative is off the top of my head, unfortunately. I had to look it up as well. Multi-resolution hash encoding. Recently, multi-resolution hash encoding, he keeps referencing his own paper here, has shown great scalability for neural scene representations, generating fine-grained details for tasks such as novel view synthesis. So novel view synthesis is different from neural surface reconstruction, or surface reconstruction, because in surface reconstruction, technically, you have pictures of the object from all views, and you're trying to reconstruct the surface, right? Novel view synthesis is kind of a different problem entirely. That is, okay, I only have pictures of the front of this object, and can you give me a picture of the back of this object, right? Like some novel view. Sometimes novel view synthesis also refers to kind of like interpolating between views that you already have, but I feel like that's kind of the easy novel view synthesis. To me, novel view synthesis is more the hard problem of like getting a view of something where you have basically no camera angle even near that. We adopt the representation power of hash encodings. Hash encodings uses multi-resolution grids, right? So grids there with an S, where you're going to have basically multiple grids at multiple resolutions. You're going to have a coarse grid, which is going to have basically the squares are going to be very big, and then you're going to have a fine grid where the squares are going to be very small. Each hash entry, right? So every time you see hash, just in your head, think Python dictionary. So each item in this Python dictionary is going to store the encoding feature. So what is that? Okay, so let V1 to VL, so this curly brackets here means the set of V1 to VL, be the set of different spatial grid resolutions. Okay, so at the beginning of this paper, we were uncertain whether they were going to have just two, whether there was going to be a coarse and a fine, but right here they're letting you know there's L, so there's L different ones. We don't know what the value for L is, but it might even be like 10. I don't know about 100. 100 seems a little bit too big, but maybe if I had to guess, probably 10. 10 different multi-resolution grids, or 10 different grids. Given a input position xi, we map it to the corresponding position at each grid resolution VL. All right, so here the word map it. Basically now, anytime you see the map it, think about in your head a Python, that colon that says here's the key for the hash entry, and then here's the actual thing that it corresponds to, what it maps to. And what is it mapping to? It's mapping to the corresponding position at each grid resolution. Okay, so the position at each grid resolution V sub L, where xi comma L is xi times V sub L. Okay, so the little l is basically where within the grid you are, which grid you are in. The feature vector gamma L, which is a function of xil, is the dimensionality of that is c. So it's some vector with c elements in it, right? That's probably going to be the output of some neural net, right? They keep using the word feature. Given resolution VL is obtained via trilinear interpolation of hash entries at the grid cell corners. Okay, so this is something that I remember seeing in Google NeRF, whatever, I'm never going to find this paper, but basically this idea that you can interpolate between the features vectors at different, that are basically encoded within a spatial grid, and you can interpolate between those and get something meaningful, right? I've seen this idea before, and it is quite interesting. The encoding features across all spatial resolutions are concatenating together, forming a gamma xi equals RCL feature vector. Okay, so you have L total grids, and then inside each of those grids, you have some point. You say, okay, I have this point, and this point is going to have a feature vector for each corresponding grid. But then all of those feature vectors, I'm going to combine them, right? Each single resolution feature vector, we're going to combine it into one feature vector that's basically the concatenation of all those feature vectors. So you see how this dimensionality C here becomes dimensionality C times capital L because there's L total sets of grids, right? And this is basically just showing you here's a concatenation. the feature at xi is equal to the feature for the resolution for grid 1 at xi all the way to grid L at xi. The encoded features are then passed to a shallow MLP. Shallow refers to the fact that there's not a lot of layers. It's not very deep. It would have been xi minus xi plus 1 in the denominator if it was a derivative. Yeah, I see what you're saying. What do they mean by a grid? Is it a 2D grid or a 3D volume? It's a 3D grid. Here, I mean, they're showing you 2D here just because it's like easy to visualize, but I think it's a 3D grid, right? One alternative to hash encoding is sparse voxel structures, so octrees. If you guys have ever seen these are really fucking cool. I had to implement an octree as part of an interview question a very long time ago, so this is a classic interview question if you guys are applying for computer vision jobs, is implementing an octree. But an octree is basically using a tree structure. So a tree is basically this, right? A graph with edges that basically expand to more edges, and you have leaf nodes and you have those kind of things, right? There's all kinds of fast graph algorithms in computer science. A lot of data structures are graphs, so basically algorithms that use graphs are very popular, and an octree is a way to represent 3D space in a graph, right? And the cool thing about octrees is that you can basically change the resolution, right? So you see here how the voxel in the corner here is very big because there's nothing in it, but then as you get into the parts of the neural parts inside the volume that actually have an object inside of it, you can see how the resolution gets finer and finer and finer. So this is called sparse voxel structures, but these are generally not very popular anymore, I would say. I don't know. Volumetric feature grids require hierarchical spatial decomposition to make the parameter count tractable. Otherwise, the memory would grow cubically with spatial resolution. Given such hierarchy, finer voxel resolutions by design cannot recover surfaces that are misrepresented by coarser resolutions. Hash encoding instead assumes no spatial hierarchy and resolves collision automatically based on gradient averaging. Yeah, so the problem with the octrees, right, is that you're basically fundamentally storing your data in one kind of grid, if you want to think of it that way, and that grid has different resolutions depending on where you are within the object. So that's different from what they're doing here, which is basically they have a multi-resolution or a multi-grid, right? They have multiple grids. So kind of all the grids are on top of each other, versus in the octree you have one grid that has different levels of resolution. All right. I'm kind of blowing through this, so like if you guys have any questions, definitely let me know. Thank you, Kalina, for asking questions, but I don't know if everybody else here is a computer vision expert or not, so definitely let me know if you guys are confused by anything here. All right, let's get into the numerical gradient computation. All right, we show in this section that analytical gradient so analytical gradient is this is when I described this earlier, but basically in my head, when I think analytical gradient versus numerical gradient, I think of numerical approximation. I think of kind of Newton's method. I think of like taking 2 points and drawing a line in between them and using that as an approximation of the gradient. When I think analytical gradient, I think of actually solving the equation and actually finding the exact value of the derivative and then the value of the second derivative and so on. But let's see what they have to say. Therefore, optimization updates only propagates to local hash grids, making non-local smoothness. What does that mean? What do they mean by non-local smoothness? So lacking non-local smoothness. Non-local smoothness probably means smoothness over coarser resolution. So maybe within each tiny little grid, the surface, right? The surface of the object is smooth, but then if you have kind of a larger, coarser grid, the surface of the object is no longer smooth. We propose a simple fix to a locality problem by using numerical gradients. An overview is shown in Figure 2. Okay, let's see. A special property of SDF is that is its differentiability with a gradient of the unit norm. All right, so the sine distance function is differentiable. Differentiable means you can take the derivative of it. And why is that important? Because in order to push a gradient, right, in order to use the process of gradient descent, which is basically the cornerstone of all machine learning, you need to have functions that are differentiable. So obviously SDF, which is something that people have been using in kind of other learning-based approaches, is going to be differentiable. The gradient of the SDF satisfies the iconal equation. Okay, so we finally figured out what the fuck iconal is, right? They mentioned iconal regularization. So here, what is iconal equation? Iconal equation is the gradient here of f of x, right? So gradient of SDF, you see this? This is what this means. Upside down triangle of f of x, and the magnitude of that is 1. Almost everywhere. So what does that mean? It means that if you took a point on that sine distance function and you looked at the slope at that point equals 1, the magnitude of that. To enforce the optimal neural representation to be a valid SDF, the iconal loss is typically imposed on the SDF predictions. Okay, so the iconal loss is typically imposed. This is what the regularization means, right? It's basically a regularization is an additional thing that you add to your optimization process in order to kind of regularize it, right? Like kind of like push it in the direction that you want, so it's a little bit better behaved, a little bit more predictable, ends up in the same place more often, right? So this is the actual loss that they're adding here, right? So far we have 2 losses here. We have our NeRF loss, this LRGB here, and then we have the iconal loss, LIC here. So this is 1 over n summation from 1 to n. So whenever you see 1 over n summation 1 to n, this is basically the average of the grad of f at xi. So at each point xi, and obviously there's going to be n total points, minus 1 squared. Okay, so basically this penalizes anything that isn't 1, right? So if the grad of f of x here, if they're saying that this is equal to 1 almost everywhere, right? Whenever this value here is equal to 1, this here is going to be 1 minus 1, which is going to be 0. So then you're going to have just the sum of a bunch of zeros, and your LIC is going to be 0, right? Which is ideally what you want. But the fact that they say almost everywhere means that sometimes this value here is not 1. Maybe it's 0, maybe it's 0.99, or maybe it's 1.01, or maybe it's 3 or something like that, right? And as soon as you have even 1.01, 1.01 minus 1 equals 0.01, 0.01 squared. Now you're adding up a bunch of things. Now this loss is not going to be 0 anymore. Now that loss is going to be actually pushing you in a direction. Holy shit. All right. Sorry, you guys sent a bunch of stuff here. Speaking of, do they mean by grid? Laplacian pyramid might be a good analogy for this set of grids. Okay. I like pyramid as a different word to describe hierarchy. Speaking of numerical grad, maybe they use it because MIPS uses the ReLU function, which is not smooth. Okay, the ReLU doesn't have a second derivative because it is piecewise, right? The ReLU has this kind of like sharp little point where it goes from being flat to being linear. I saw a paper that optimizes NNs using numerical Newton because analytical Hessian is equal to 0 for ReLU. Okay. Hessian is technically usually the second order derivative, so the second order derivative of the ReLU is 0. Funny equation, numerical things work through numerical says it shouldn't work. Yeah, numerical methods feel like they shouldn't work, but they do work in practice. No, the reason for numerical grad isn't because of that. They explain why the numerical gradient. Guess this is an inexactance of gradient computation. Okay, I think we're getting ahead of ourselves. Not only do they have a very nice looking figure, but they also have this little thing here. So hopefully this little GIF allows us to fully understand exactly why they're doing the numerical gradient here. Where n is the total number of sampled points. Okay, so to allow for end-to-end optimization, a double backwards operation on the SDF correction is required. So double backwards, I think this is where the double derivative is coming from, the derivative of the derivative, right? That's where maybe the numerical stuff is required. The de facto method for computing surface normals on a SDF is to use analytical gradients. You see that? So you have a surface, you have a sine distance function which represents a surface, and you want to get the normal. But in order to get the normal, you basically need to know the shape of that surface, right? You need to know exactly where that normal vector should point. And if you just have a single point, you don't know what the surface looks like, right? If the surface is like this, the normal is going to be this way. The surface is like that, normal is going to be that way. So that's what they're saying here, is that in order to get the surface normals, which I think is what they really want, really all of this is just a way to get the surface normal, they need to basically get this double derivative, this double backward operation. And in order to do that, normally you would use analytical gradients. Analytical gradients of the hash encoding with respect to position, however, are not continuous across space under trilinear interpolation. All right, this is a dense sentence here. Are not continuous across space under trilinear interpolation. So I think what they're talking about here is that they're interpolating between these feature vectors, right? So they have these feature vectors, and they have a bunch of these feature vectors. They have one for each grid. So you have a kind of you have L of these different grids at different resolutions, and then you're getting a feature vector for a point in each grid, and then you're basically interpolating all of those feature vectors together. So the problem is that whenever you do this interpolation, that is not going to be continuous. You can't get the derivative of that, because you're basically going to have a value, and then as soon as like one of the values underneath changes, it's going to suddenly change, right? So let's say that you have two big, the coarse grid has like two big areas of squares, right? So right on one side of the square, on one side of the big square, the value of the feature vector is going to be one thing because you're interpolating with the feature vector for this square. But then as soon as you cross that boundary and you start interpolating with the feature vector for this square, you're going to have a discontinuity there, right? The value of that is suddenly it's going to be discontinuous. So that's what's making this derivative hard, right? It's hard to get the shape of that surface, and because you can't get the shape of that surface, you can't get the surface normal. Okay, so this is starting to make more sense to me. To find the sampling location in a voxel grid, each 3D point xi. Okay, I like how they defined the 3D point xi 10 times. I prefer that, like it would have been very easy for them to just say xi and then they just like never mention it again, and then we have to keep scrolling back to the original definition. But like, I like the fact that all their notation is consistent, and not only is it consistent, but it's also they keep redefining it just so you don't have to go back to an earlier part of the paper to read it. Would be the first scaled by the grid resolution VL. So obviously there's different grid resolutions. There's L of these grids, written as XIL, XI times VL. Let the coefficient for trilinear interpolation be beta. What the fuck is this little symbol? Oh, rounded positions. Okay, so we denote that the rounding operations are non-differentiable. So, okay, so this little L and then this little, I don't know, what is that? Square bracket without the top and then square bracket without the bottom. Those are rounding, so it's like a function that basically you round it. And, right, remember back here when we were saying that in order to do gradient descent and pretty much all of machine learning, you need to use differentiable things. And this is a huge problem because these rounding are non-differentiable, right? What's the derivative of a rounding function? That derivative is, you can't really calculate that. Okay, so they have a coefficient, which is basically the value at a thing minus the rounded value of that thing. So basically, how much are you rounding off or on? The resulting feature vectors are this. So you have your gamma L feature vector, which is the concatenated feature vector, right? It's concatenated for each L. You have the feature vector at the rounded point times 1 minus beta plus the feature vector at the rounded opposite point. I don't know if which one is which. I'm assuming this one means floor rounded, so basically you get rid of the decimal, and then this one means ceiling rounded, so it's on the other side. So basically here you would have a point, and then let's see if we can get to this, right? So the one rounded point would be here, and then the other rounded point would be here. So basically these 2 points here refer to the within each grid, which is the point to the left of the point that you want and which is the point to the right of the point that you want, and then basically 1 minus beta between those. So you're interpolating. This is literally a interpolation between the 2 points, the 2 feature vectors on the points of the grid that straddle the point that you're actually interested in, which is xi of L. Okay, as a result, the derivative of hash encoding with respect to the position can be obtained as this. Okay, so now what they want is they want the partial derivative of this feature vector, gamma L xil, with respect to the position, right? And in order to do that, they use the little chain rule here, and they basically do dxi for all of this crap here. Obviously, because beta is a function of xi, you're going to have to basically go into it here. So now you have the partial derivative of beta with respect to xi, the partial derivative of beta with respect to xi, which is actually pretty easy because this value should just be a number, right? So the partial derivative of this with respect to that is basically just 1. And then I guess this value is the hard part. This is the tricky part here. Where's this V coming from? VL. Grid resolution. Okay, so basically you end up with the feature vector at the part of the grid leftmost of your point and the feature vector at the part of the grid rightmost of your point, each multiplied by the resolution of the grid. Holy shit. All right, there we go. The derivative of the hash encoding is local, i.e., when xi moves across cell borders, the corresponding hash entries will be different. Yeah. So because you have these values here, which are going to change, right? As soon as you cross over a point, or as soon as you cross over from one grid or one cell in your grid into another cell in the same grid, there's going to be a discontinuity in that derivative of the hash encoding. And that discontinuity is going to be gross. Therefore, the iconal loss is defined in equation 5 only backpropagates to the locally sampled hash entries, i.e. these two things. Locally sampled there, obviously, because you have some hash map that allows you to say, okay, at this point in this grid, what is the value of the feature vector, right? We saw up here, they told us the multi-resolution grid, each hash map here is mapping from the position xi to the feature vector. To ensure consistency in surface representation, okay, wait up. These grid cells should produce coherent surface normals without sudden transitions. I agree with that. To ensure consistency in surface representation, joint optimization of these grid cells is desirable. However, the analytical gradient is limited to local grid cells unless all corresponding grid cells happen to be sampled and optimized simultaneously. Such sampling is not always guaranteed. I feel like my brain needs a second to parse exactly why this is not. So such sampling is not guaranteed. Really, I guess what they're saying here is that you're not going to sample, the points that you sample are not necessarily going to be in the grid cells that are right next to each other. That makes sense to me. But why would you be able to take the analytical gradient if you had all the points in all the grid cells? I guess because the grid cells change. So the problem is that as you're training this, right, you're going to be pushing gradients, but you're only going to be pushing gradients into the ones that you sample, right? So if you wanted to use the analytical gradient, you'd have to basically make sure that at every step and at every kind of gradient update step, you're changing the value at every single one of the grid cells, but you're not doing that. So yeah, this is what they mean by simultaneously. To overcome the locality of the analytical gradient of a hash encoding, we propose to compute the surface normals using numerical gradients. If the step size of the numerical gradient is smaller than the grid size of the hash encoding, the numerical gradient would be equivalent to the analytical gradient. So I think this sentence right here is kind of the TLDR of all this numerical versus analytical gradient stuff. Otherwise, hash entries of multiple grid cells would participate in the surface normal computation. Backpropagating through the surface normals thus allows hash entries of multiple grids to receive optimization updates simultaneously. Intuitively, numerical gradients with carefully chosen step sizes can be interpreted as a smoothing operation on the analytical gradient expression. Okay. I think it's time we look at figure 2 here. Using numerical gradients for higher order derivatives distributes the backpropagation updates beyond the local hash grid cell. Okay, so you have forward passes, the blue. So forward pass is going to be inference. Forward pass is whenever you're determining what you're basically forward passing, and you're saying, okay, what is the feature vector at this point in the grid, right? You have, this is one of many grids. So they're just showing you here in one grid, but there's going to be L of these. You're getting the actual vectors. Your X is the interpolation of those. And then you have some loss like way down the line where you're basically going to be saying, is this look like the image? And then that loss, which is saying, does this look like the image, goes through a bunch of crap and eventually gets to here, right? And once it gets to here, it's saying, okay, well, now I need to update the little feature vectors here such that they make all the way down the line things look more like the image. So in the analytical gradient, you need to basically, you can only push it here, I guess. You can only calculate it for these two. And then, which means that this one over here and this one over here are going to kind of get left behind, and they're not going to be very, and you're going to get this kind of like weird kind of issue because these are going to be updated separately from these. But the way that they do it is they say, okay, you add and remove this little sigma here, or epsilon, sorry. This is like the 50th time I have looked this up. It's lowercase epsilon, right? Yeah. No. Okay, so you add and remove this epsilon. You're in two different grid cells now. You can now push gradients on all four of these little vectors here. Beyond the local hash grid cell. Right, so analytical gradients, you can only push updates here, versus with the numerical gradients, you can push updates beyond just the single cell. You can push it to the cells around it as well. An alternative to normal supervision is a teacher-student curriculum where the predicted noisy normals are driven towards MLP outputs to exploit the smoothness of MLPs. However, analytical gradients from such teacher-student losses still only backpropagate to local grid cells for hash encoding. In contrast, numerical gradients solve the locality issue without the need of additional networks. Okay, so basically there's some other approach where as soon as you see teacher-student, that means multiple neural nets, where the student neural network is basically trying to mimic the teacher-student or the teacher neural network. But whatever that approach is, it's shit because you need multiple MLPs, and they're saying that in this paper, using the numerical gradients, you can solve this locality issue without having to have multiple neural nets. Okay, so let's actually look at this. maybe those vectors are like vertices of a surface. Adjacent vertices represent polygons, which have ugly normals. Second derivative of analytical computation gives 0. Use numerical method. Joint optimization is desirable. Remember that computing normal a vertex of a mesh is tricky, as a vertex does not represent a surface, right? A vertex has that same kind of discontinuity that you were talking about with the ReLU. But computing a normal on a polygon is easy, so if the optimization process jumps exactly on a single vertex, then it's kind of bad. Yeah, this paper is kind of intense, but okay, so you have a point X in a grid. You basically find a bunch of nearby points with some sigma, or epsilon, sorry. Then you sample for each point, right? So this point is going to be the interpolation of these points. All right, that makes sense. Finite differences. So this thing here that they did with those green dots, like in your head, that's basically this. So you see here how they're trying, whenever you're like, okay, well, what's the derivative at this point? And you're like, well, shit, I don't know how to analytically compute the derivative of this red line. I have no idea what the fuck this is. And you're like, okay, well, why don't we use this numerical method? And in this numerical method, you just got to tell me what the value of the function is here, and you got to tell me what the value of the function is here, and then we're going to basically draw these lines, and I'll tell you roughly what the derivative there is, right? So that's the Newton's method. And this is basically the same shit, but in 3D, even though here they're showing you in 2D. So each one of these green points here is basically this here, right? It's like this x2 and this x0 point. Or I guess maybe x0 is the one that you actually want, and then x1 and x2 are the ones that you are sampling. But either way, those are the numerical the points that you're sampling for the purpose of the numerical gradient calculation. And maybe one thing that's confusing there is that they use the word sample to refer to these points that they're using for the numerical gradient calculation, but the word sample is also used to refer to sampling in a NeRF, right? So when you're selecting points along this ray in a NeRF, you call that sampling as well. So there's a little bit of confusion there with overloading the word sample, but it's two different types of sampling there. There's the sampling that you're doing in terms of points along the ray of a NeRF, and then here there's the sampling that you're doing around a point so that you can calculate the numerical derivative. Okay, so using numerical gradient optimizes the hash grids beyond the local cells and acts as a smoothing operation on the SDF. Okay, so basically, if you were to do this analytically, you would eventually get a gradient for these 4 points right here, right? These 4 points, these local points, the local cell of this point, right? But because you're using numerical gradients, right? Now you're not just pushing gradients into these 4 points here, you're pushing gradients into these, whatever this is, what is this? 2, 4, 6, 8, 10, 12, into these 12 points here, right? So now, because you're updating this whole area around this point, you're basically smoothing. It acts as a smoothing operation because you're kind of updating a whole area around it, right? You're fundamentally making the thing more smooth. Versus if you were to do it analytically, you would only update these 4 points, and then maybe you would only update these 4 points up here some other time, and then eventually you would end up with this kind of like jagged kind of you would end up with these kind of like discontinuity kind of things, right? Okay, I think that makes sense to me. To compute the surface normals using the numerical gradient, additional SDF samples are needed. Given a sampled point xi, we additionally sample 2 points along each axis of the canonical coordinate around xi within a vicinity of a step size epsilon. So that's here, right? So they sample 2 additional points per dimension. So obviously this is a 2D image, so they're showing you the x. They're sampling 1 in x, 1 in y, but there would also be 1 in z, right? So this is a 3D volume, so there would be a total of 6 points that they sample, 2 for each axis. For example, the x component of the surface normal can be found as this. Yeah, using the numerical method kind of guarantees that you don't compute the gradient exactly at the vertices because it adds the delta to the vertex coordinates. Yeah, I could see that. So basically the gradient with respect to x, right? You have the xi position. You're adding and subtracting this epsilon. So that's the adding epsilon, subtracting epsilon. You're dividing by that epsilon. And this is your numerical estimate of what the gradient there is. In total, 6 additional SDF samples are required for numerical surface normal computational, right? So there's 3 dimensions of space in our reality, which means that you have 3 axes. Each of those axes is going to have a plus minus, so you're going to have 6 total points that you sample. Looks good to me. Which actually makes you think there's actually probably a better way to do this, right? You don't have to limit this to 3 points. You could probably do this with more points, right? You could do this not just with because when you're doing this, you're kind of fundamentally making this prior where the x-axis, the y-axis, and the z-axis have like some kind of special meaning, right? Your grid is aligned to the x, y, z. But what happens if you took that grid and you just rotated it 45 degrees, right? You would probably end up with something completely different. So I could see taking this paper and then just doing it with one set of grids that are aligned to the X, Y, Z, and then another set of grids that are rotated by 45 degrees, and maybe you could get more out of that. Course-defined optimization can better shape the loss landscape to avoid falling into a false local minima. This is the pinnacle of deep learning right here, machine learning, is that anytime you use a kind of gradient-based optimization method, you can fall into local minima, right? What people refer to as the loss landscape. I love this picture. Oh shit, I just poured coffee all over my keyboard. Fuck. Give me 10 seconds. Sloppy today. I think it's because I didn't drink enough coffee. I think I'm just going to deal with this later. My poor keyboard. All right, I'm back. Loss landscape neural nets. Yeah, this paper is really fucking good. If you guys are interested in papers, this is like one of my favorite papers where basically they look at the loss landscape of neural nets. But this is what you should think of when you think of loss landscape. And then what you're doing when you're doing gradient descent is your little neural net represents a little point in space somewhere here, right? And every time you update the weights of the neural net, you're basically just taking a little step over here. And when you get the gradient is telling you, okay, the gradient of this loss is telling me to go that way, right? And basically what it's doing is it's basically just telling you what the surface is like, where is down, right? So it's like, okay, I should move this way, 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 right? So all you're doing is just taking little steps in this loss landscape. Let's see if we can find a nice picture of this. I think maybe down here. Yeah, and this paper mostly just talks about how you can use skip connections or residual connections as they're known, and those residual connections make the loss landscape a lot smoother, which means that it's easier to use gradient descent to get to the actual minima that you want, right? The global minima. Even though in reality you're basically never getting to the global minimum, right? You're always in some kind of local minima, but some local minima are better than other local minima, right? You definitely want to be in this local minima down here, right at the bottom of this deep channel, rather than the local minima here, right? Like, let's say you get stuck right here, and then you take a gradient step, and you say, okay, actually go back, and then you take a gradient step, and then go back, and then gradient step, so like you kind of get stuck in this little circle here. So you want to better shape the loss landscape to avoid falling into a false local minima. Such a strategy has found many applications in computer vision, such as image-based registration. Neuralangelo also adopts a course-defined optimization scheme to reconstruct the surfaces with progressive levels of details. Using numerical gradients for the higher-order derivatives naturally enables Neuralangelo to perform course-defined optimization from 2 perspectives: step size and hash grid resolution. All right, so basically what they're saying here is that your coarse define, right? Your kind of multi-resolution, like hierarchy kind of concept is coming in through two different variables here, right? At some point, you have to choose what the value of this epsilon is, right? Which defines the size of the step that you're taking, right? That little epsilon step. You need to pick what the value of that is, and then you also need to pick the resolution of the grid. So you need to pick the value of like how big is every single one of these squares, right? Like what is the dimension of that? So those are two hyperparameters that you can play with to get a coarser resolution or a faster or a finer resolution. Numerical gradients can be interpreted as a smoothing operation where the step size controls the resolution and the amount of recovered detail. Imposing the icon loss, which is the one up here, iconal loss, I don't even know how to pronounce that, with a larger E for numerical surface ensures the surface normal is consistent at a larger scale, thus producing consistent and continuous surfaces. Right, so at the larger scale, you want consistent and continuous surfaces. At the smaller scale, you want smooth surfaces. We initialize the step size to the coarsest hash grid and exponentially decrease it, matching different hash grid sizes throughout the optimization process. Okay, so basically, of course, makes a ton of sense, but the step size is going to largely depend on the size of the grid, right? So even though we have two parameters here, we have this epsilon and we have this v, really we only have one parameter, which is the v, because your epsilon is largely going to just fall out of whatever you choose for your v. If all hash grids are activated at the start of the optimization, to capture geometric detail, fine hash grids must first unlearn from the coarse optimization with a large step size epsilon and relearn with a smaller epsilon. Okay, so it seems like they're actually doing a multi-step process here where first all hash grids, which means all the grids, even the ones that are even fine resolution, use the larger step size, but then they also use the smaller step size. We only enable an initial set of coarse hash grids and progressively activate finer hash grids throughout the optimization when epsilon decreases to the spatial size. Okay. So the way that this is going to work is they're going to basically have the large grids first, and then as they go further and further and further into the optimization process, they add increasingly finer and finer grids, which is actually great because it means that you can get a quick and dirty version of it pretty very quickly, but then you can, as you spend more and more time optimizing, you can get a finer and finer and finer version. So it gives you a very clear trade-off between the time you spend optimizing and the kind of fine, the resolution of the tiniest grid that you're going to use. In practice, we also apply weight decay over all parameters to avoid single resolution features dominating the final result. So weight decay is something that people use in neural networks. It's basically, you think of every single time you push gradients, right? Your little neural net is composed of all these little neurons. They have some weight value. That weight, I don't know, maybe it's like 0.123. And then every step you do weight decay. So that little weight value goes from 0.123 to 0.122, and then 0.121, and then 0.120. So over time, unless those neurons are being used and the kind of the value that's coming out of them is actually being useful, their little weight value is just going to decrease and decrease and decrease and decrease and get smaller and smaller over time. So weight decay is a very common kind of regularization that you use to prevent to ensure that the activations and that the kind of features that are inside your neural net are actually useful, right? And you're not just kind of like they were useful at the very, very beginning of your optimization, and then like by the time you get to the end, they're just kind of worthless, but they're still there because you're not using weight decay. But weight decay is kind of a double-edged sword. Sometimes it's not, it doesn't help you, and it actually doesn't help, and then you actually lose performance by using it, so it's a very finicky hyperparameter. To further encourage the smoothness of the reconstructed surfaces, we impose a prior by regularizing the mean curvature of the SDF. Okay, so not only do they have a prior here that they're using to regularize based on this idea that the iconal equation should be equal to 1 as pretty much as everywhere, right? That's what this loss is doing, is it's trying to make the iconal equation equal to 1 everywhere. They also have an additional regularization loss here where they're saying, okay, the second derivative here, or second gradient, curl, I think this is usually called, curl. Ooh, let's come here. What the fuck? Control T, curl. Oh, my keyboard's broken, that's why. Oh no, I can't even type. Curl of, oh my god, all right. I'm unplugging my keyboard. I'm gonna have to do this entirely with just my mouse, but I think this is usually called the curl. I can't even zoom in. We note that the samples used for the surface normal computation are sufficient for curvature computation. The total loss is defined as the weighted sum of losses. So the loss that you use at the very end is basically you sum together your icon loss, this curvature loss, and each of those has some hyperparameter W_IC and W_curve, which is going to determine how much of an impact they have on the actual true loss that you want, which is this RGB, right? This is the one that you actually care about, this LRGB. All network parameters, including MLP and hash encodings, are trained jointly end-to-end. This is good. You want end-to-end learning. You don't want these like multi-stage pipelines because that just makes it way harder and more annoying. Curl is something from physics. Yes, that is my original undergrad. Second derivative of the surface, literally curvature. There you go. The curvature of space-time, right? So whenever people say that, the curvature of space-time, that's what they're referring to. Following prior work, we conduct experiments on 15 object-centric scenes of the DTU dataset. Okay, so now they've explained their method, and now they're going to go into the experiment section where they're going to basically evaluate how good they are. Each scene has 49 or 64 images captured by a robot-held monocular RGB camera. Okay. So this is a little bit of cheating. So monocular RGB camera, that's a single RGB camera, but it's robot held. And why would you want a robot to hold the camera for you? The reason you would want a robot to hold the camera for you is so that you know exactly the position of the camera, right? If you're sitting there with your cell phone and you're kind of like recording like this, like, yes, your cell phone has like a approximate position based on the accelerometer and the gyro, but the position that you're going to have whenever you actually do this optimization process is going to be a little bit coarse, right? It's not going to be very good. There's going to be errors in it. But if the robot is holding the camera, robots are very, very accurate, right? A modern robot arm, it knows exactly where it's like sub-millimeter precision on robot arms, right? So that means that the positions that they're going to be using for this optimization process in terms of the camera positions is basically perfect. The ground truth is obtained from a structured light scanner. Okay, so if you have an explicit depth sensor like a structured light scanner, you can basically get you can use traditional photogrammetry techniques to basically get the surface of the object, and they're going to call this ground truth, even though really it's not ground truth, right? It's a approximation of ground truth based on a different approach. We further conduct experiments on 6 scenes of the tanks and temples dataset. Okay, so I think this is probably the picture that they showed at the very beginning here, right, of this like kind of like temple looking thing. So that's probably that. Including large-scale indoor and outdoor scenes. Each scene contains 263 to 1,107 images captured using a handheld monocular RGB camera. So this is much harder, right? So here, 49 to 64 images captured by a robot-held monocular RGB camera. This is going to be very accurate positions. Here, 263 images captured using a handheld monocular RGB camera, much less accuracy on the camera images, but you have more images, so maybe it kind of balances out. The ground truth is obtained using a LiDAR sensor. Again, this isn't really ground truth. This is just an approximation based on explicit depth, which is also going to have some amount of inaccuracy. So take that as you will. How would you get the ground truth? Well, you would get the ground truth by having someone sit there and like literally measure it with a little measuring tape, and then perfectly create a 3D representation of it. Our hash encoding resolution is 2 to the 5 with 2 to the 16 with 16 levels. Okay, so we finally get the resolution of the number of grids. So there's 16 total grids, which is kind of intense. Each hash entry has a channel size of 8. Okay, so total 8 is the dimensionality of the vector. So here, if you remember the, where is it? Up here, right? The encoding features across all spatial resolutions are concatenated together. So at every single point in your grid, you're going to have a vector which represents the feature at that point. And what you're doing is there's L of these. So they said 16, L equals 16, and then C, which is the dimensionality of the individual feature vector, is 8. So 6 by 18 is the dimensionality of the concatenated feature vector at each point. Each hash entry has a channel size of 8. The maximum number of hash entries of each resolution is 2 to the 22. What does this mean? We activate 4 and 8 hash resolutions at the beginning of optimization and tanks and due to the differences. Okay, so they said also earlier that they start with a lower amount of grids and then they increase the amount of grids as you go on further, right? So they start with the coarse grids and then they add the finer grids. So they're starting with 4 and 8 grids. And actually this isn't necessarily great because the fact that they're using a different number of starting grids depending on the data set is a little sketchy, because anytime you have hyperparameters that are dependent on the actual data set, that's no good, because it means that whoever uses this technique is going to have to choose a value for those hyperparameters that corresponds to their data set, and they might not have the same intuition. They might not be able to pick the right one or the right value. We enable a new hash resolution every 5,000 iterations when the step size equals its grid size. For all experiments, we do not utilize auxiliary data such as segmentation or depth. Yeah, so kind of strong point of this paper is that they don't use auxiliary data, so you bet your ass they're going to be telling you all about that every time. We report chamfer distance and F1 score for surface evaluation. These are just basically metrics to determine how good your surface is. And we use peak signal-to-noise ratio to report image synthesis quality. So these chamfer distance and F1 score are for the quality of the surface, and then signal-to-noise ratio is for the quality of the image. Right? So PSNR is basically the 2D image, and then the chamfer distance is like how good the actual surface is. Did we look at this? Okay, so here we go. So we start here. Coarse define for progressive levels of detail. So you have N total, or L total grids, right? So there's going to be 16 total. You start off with 4. You start off with a big step size, right, to do this numerical gradient calculation. And then they said they were decreasing the step size over time, right? So as you get further and further in the optimization process, the step size goes down, right? And you start from just the coarse grid. So this is what they're showing you. And then you get to a certain point and you add the next grid, right? So here's the next grid. And your feature is now, first it's just the coarse grid feature, but then it becomes this concatenated coarse and finer grid. And then more, you get even finer grid, and you get the feature becomes even more, right? And so on. That feature gets fed into the MLP, this multi-layer perceptron, which is going to give you two things. It's going to give you the color. I think there's actually two. There's an MLP for the color, and then there's an MLP for the sign distance function. So the MLP for the color will tell you at any given point in space what's the color of that point. The MLP for SDF will tell you at any given point in space how far away are you from the surface of the object in that. So here they actually show you what that looks like in practice. So here you have at a hash grid resolution of 4. So there's 4, then 8, then 12, then 16, and then it stops at 16. Pretty cool. Okay, DTU benchmark. We show qualitative results. Achieves the lowest chamfer distance and highest PSNR. Further ablate against the following conditions. Okay, so they do use the analytical gradients. They do a couple different ablation studies here. So ablation studies are whenever they try their same technique but with a couple different modifications, and then in order to do, the point of doing that is that they want to be able to tell which parts of their technique are the ones that are resulting in the biggest kind of bang for the buck. So they talked about analytical gradient versus numerical gradient. Of course, they're going to compare. They're going to try a variant of the analytical gradients, which they call progressive activation, and then NG for numerical gradients. Okay, so here you have the results from all of these. So this is like a picture of a house. I guess this is what the ground truth should be, and then this is showing you that. I can see how this is more smooth, right? Look at the numerical gradient is smooth. But the analytical gradient has like more of this brick texture, which maybe that's a good thing. Maybe you want the brick texture. I don't know. While numerical gradients lead to a better coarse shape, details are also smoothed. Okay, but then the way they, so AG, NG is analytical versus numerical, and you have the very clear kind of like not smooth and smooth, but sometimes the smooth is a little bit too smooth. So the way that they fight that is with the progressive, right? So this progressive hash resolution that they do, where like at the beginning of the training, they start with just the coarse one and then they add the finer one over time. Okay. Qualitative results, quantitative Neuralangelo achieves the best reconstruction quality. I like this. So just a meta point on papers, like sometimes they tell you whenever you're writing papers to not use colors, because kind of the common argument that you hear time and time again is like, oh, sometimes people print out the paper and then they read it, and oftentimes people don't have color printers. So if you have colors inside the figures and tables of your paper, then people aren't going to be able to see those colors. But I don't know, I feel like that applied maybe 20 years ago, but like in 2023, like I think 99.9% of the people that are reading your paper are going to be reading it on a monitor, which means that they're going to have access to color. So why not color the things like this? You know, this is very nice. I like this. I like the green is the best and blue is the second best. And I don't know, this seems like they knocked it out of the park here. It's best on pretty much every single metric here. They compare it to a bunch of different things. NeRF, volume SDF, noose, HF noose, regular SDF, neural warp. I don't know how much better this is. I don't know if these numbers seem pretty good, but I don't know exactly, right? It's like, is 0.37 compared to 0.6? Like, how much better is that? I don't really know. But they are the best. Uh, 2 to the 11th is 2048 side of a volume. That's intensive. Training this thing would be extremely memory intensive. Yeah, they still haven't actually told us what they trained this on, so we'll see. Maybe, I hope they tell us. Maybe it's 7 million A100 GPUs in parallel. They might even have trained this on H100s, right? Because this is an NVIDIA paper, so I don't know if researchers at NVIDIA have access to the H100s yet. They might. As no public result is available, we train Noose and Neural Warp and report the classical multi-view stereo results using Colmap. Colmap is an old computer vision approach that gives you the position of basically all the cameras in a video. But it's kind of a huge pain, to be honest. There's like a Python package specifically for it, so if you guys are interested in that, check that out. I would open up a new tab, but my keyboard is broken, so I have no keyboard. Comparing against Noose, we recover high-fidelity surfaces, dense surfaces generated. We also find that Neural Warp often predicts surfaces for the sky and background. That's no good. Blah, blah, blah. Reconstruction looks good. Level of detail. Progressively optimizes the hash. We inspect the progressive level of detail. Yeah, so one concept from the game world and movie world, CGI world, this is just the 3D world, is basically this idea of level of detail. So in a lot of video games, assets, right, will be stored at multiple levels of detail, which means there's a version of the asset that's very coarse and blocky, and then there's a version of the asset that's very high resolution. And as you get closer to that object in the game world, the actual object changes and you get a finer and finer and better version of it, right? You don't want to be loading the 4K texture, like 700 million vertice version of a tree whenever that tree is like 200 feet away from you in the game, right? You want to load the shitty version of the tree, and then as you get closer and closer to it, you load the faster version of the high resolution version of the tree. So it does seem kind of cool that because their technique has this kind of like multi-resolution grid and they can kind of like piecemeal increase it, they kind of naturally get this LOD, right? They naturally get like a level of detail. They get multiple versions of the asset at different kind of levels of detail, which is maybe the whole reason they did that. We note that flat surfaces are predicted at sufficiently high resolutions, thus only relying on the continuity of local cells to coarse resolutions is not sufficient. This result motivates the use of numerical gradients such that black box propagation is beyond local grid cells. Okay, so here you have the different levels of resolution. Qualitative results on the tanks and temples. Ablations, curvature regularization. So with or without this L curve that they add, let's see. Without L curve, we find that the surfaces tend to have undesirable sharp transitions. Okay, so the L curve regularizes the curvature, which is what we wanted, I guess. Topology warm-up, initialize the SDF approximately as a sphere, right? So your sine distance function, here they say they initialize it as a sphere, which means that you kind of have this object-centric kind of prior, which is actually very common in SDFs, where it's like, usually when you have an asset or any kind of 3D thing within a volume, usually it's like there's like a thing in the center and then the edges are pretty much always empty, right? Like if you look at this octree, right, like almost every single example in this Google Images is like there's this kind of object-centric kind of prior where there's an object right in the center of it and like everything. So you can kind of use a prior that gives you that object-centricness in 3D, and it's generally a pretty good prior, and that's what this is, right? The kind of a sphere in the center. Blah, blah, blah. Using L curve also makes concave shapes difficult to form because L curve preserves topology by preventing singularities in curvature. Yeah, so this is kind of a trade-off. Sometimes when you have these regularizations that add smoothness, you lose detail, and that's kind of what they were showing you here, right? Where like technically this little area of the building here is made of bricks, so the bricks are inherently discontinuous, right? There's kind of sharp edges as you kind of go from one edge of the brick to the other edge of the brick. But if you have all these priors that are kind of like trying to push you into a smooth area, right, trying to make everything smooth, you're going to lose that detail. So sometimes these like surface curvature regularization is not necessarily helping you. Sometimes it actually hurts you because the object that you're actually trying to model isn't smooth. It actually has sharp edges. So here they use a short warm-up period that linearly increases the curvature loss strength. Okay, so that's kind of cool. So what do they do? So if you remember here, the final loss that they use for the entire process is LRGB plus some weight times the L-Ike plus some weight times the L curve. And what they're saying is that when they actually start the optimization process, this W curve is actually very small. So there's almost no regularization for the curvature. And then only once you get to like the later stages of the training do you start to increase this W curve, and then the curvature regularization becomes more and more impactful, right? So there's a schedule on this W curvature. Just another hyperparameter that you have to know, right? Like, what if you had a quadratic linear or quadratic schedule for this curvature loss strength? I don't know. Conclusion: we introduced Neuralangelo, an approach for photogrammetric. Is this even a real fucking word? I feel like I would have used photogrammetry based, or I would have just said neural surface reconstruction. I don't know why they have to say photogrammetric. I guess it's because they're doing it from photos, but like, okay. The finding of Neuralangelo are simple yet effective, using numerical gradients for higher order derivatives and a course-defined optimization strategy. Neuralangelo unlocks the representation power of multi-resolution hash encodings for neural surface reconstructions modeled as SDFs. We show that Neuralangelo effectively recovers dense scene structures of both object-centric and large-scale indoor-outdoor scenes with extremely high fidelity, enabling detailed large-scale scene reconstruction from RGB videos. I mean, this was always possible, but it's always just been a question of trading off performance and how much extra data you need and how much time it takes. Our method currently samples pixels from images randomly without tracking their statistics and errors. Therefore, we use long training iterations to reduce the stochastics and ensure sufficient sampling of details. Samples pixels from images randomly. So whenever they're taking images to get the points, to get the color values at those, right, the RGB loss, which is the primary loss that they're using, is based on the difference in the pixel color here and the pixel color in the actual image. So they sample pixels randomly from those images. It is our future work to explore more efficient sampling strategy to accelerate the training process. Yeah, so you could have more complicated sampling. You could, rather than saying, okay, well, we have, what is it, 1,000 or 200 images of this, where is it here? 263 images of this building from a variety of different things, and we're going to sample random pixels out of every one of those 263 images. You could probably do something more clever where you sample from the same area of the images, or maybe you sample from images that are close together in like time, right? I don't know. There's definitely optimization or improvement to be done there. No appendices section, so I guess that's kind of it. What are we at? 2 hours? All right. Let's do a quick summary here. So, no info used on compute, yeah. Yeah, they probably used an illegal amount of GPUs, a haram amount of GPUs. They literally don't, I don't think the word GPU is in this paper. Yeah, they don't mention anything about the GPUs. They don't mention anything about the training. That's a little weird, right? Because you would think that the whole, like, NVIDIA would want to do that. NVIDIA would want to tell you, like, hey, we trained this on an H100 and it was so fast because we trained it on an H100. Like, you want to buy H100s too, don't you, right? But they didn't. They didn't tell you. So maybe they trained it on something even more next level. Maybe they trained it on a new type of GPU that they haven't even announced yet or something like that. But I don't know. I don't know why they didn't announce it. It seems like they should be showcasing that. All right, but back to the actual summary here. So we read Neuralangelo. This is a neural surface reconstruction paper from NVIDIA, where they're basically trying to create a mesh, or in this case, it's a sine distance function. So they're combining a sine distance function with a NeRF, where you're using a neural network to represent a color within a volume of space. They're using this trick where they basically break up this volume of space into these different grids, and each of those grids, they can do it at multiple resolutions, right? So they have this multiple grids of different resolutions, and inside each of those grids, basically on the vertices of those grids, you have basically these feature vectors, which you could think of it like the representation of what is inside that volume of space at that particular point in the space, right? And obviously, the lower resolution grids, the coarser resolution grids, are going to have a slightly different representation of what's in there than the finer resolution grids, right? The finer resolution grids, the feature vectors in those are probably representing the like kind of fine details, the textures, versus at the higher resolution grids is probably representing just simple things like, is this occupied or is this not occupied? But I think the main trick that they do in this paper is they basically, rather than using an analytical gradient computation, where you would basically push gradients into these four dots here, they use a numerical gradient calculation, which allows them to kind of push gradients into more of the surrounding dots. And by doing that, they kind of get a smoother surface. They have a couple different regularizations here. They have this iconal loss, and then they also have a curvature regulation here that ensures smoothness. And it's actually relatively simple in terms of training. Basically, they start with very coarse resolution, and then they no curvature loss, and then as they go further and further in the process, they add more resolution by just literally adding more of these finer resolution grids, and they start to ramp up this curvature loss. In terms of the results, they seemingly get really good results, but I don't know if this represents necessarily all of the best stuff. I'm sure there's probably other papers out here that achieve better results. And yeah, it looks really good to me, at least from these pictures. Things I don't like about this, I don't like the fact that they didn't tell us anything about the training. You know, they didn't really tell us what they trained it on, how long they trained it for, and what it cost them to train. But other than that, very cool little paper, and I very much like these little GIFs. This is like my favorite part of the paper was these little GIFs here. You know, like look at that. This is what I get excited about. Look at this little animation. So beautiful. But that's it. Thank you for listening. I think tomorrow we're going to be doing a little bit of programming. We're going to be working on our Discord bot that we've been working on for this community, for the Discord community. If you're interested in that, feel free to drop by. If you're not, feel free to recommend papers, and we'll read papers the rest of the week as well. So thank you for listening. Like and subscribe, and see you guys later.